So they give us, in this case, we get these two. Y is greater than or equal to x squared plus 6x plus 1, and y is less than or equal to negative 0.1x squared minus 1.4x plus 2.1. So we got to find which of these graphs corresponds to that stuff. Now, one thing you might miss on this, if you're not careful, is that the graphs scoot off to the right like this. Did you see that? Okay, because sometimes people aren't used to that. So, look for that. So there's lots of them off to the right. Okay, now how do we do this on our calculators? We have our calculators. This is the graphing calculator part. True, y equals, but before we maybe even do that, what do we? Well, I guess we can check and see it for it. Okay. Do I need to do something?
Clear that out.
Inequality. Yeah. You've got to go to inequality. So let's clear this guy, and then I'm just going to go. There you go. Going to go apps, and then for me, I got to go down quite a ways. I've got a lot on there. So I go alpha I, skip down to the i's, inequality, press any key, and I'm in. Okay, now in inequality, do you remember what the button is I have to always push? What's the key I have to push? The alpha, yeah. If ever I want to do any of these soft keys here, these virtual keys, I have to hit alpha first. So I'm going to go. Let's see, what are my? Find my. Okay, there are my inequalities. So I want to do a greater than or equal to. So alpha, this guy, x squared plus 6x plus 1. And then I've got y is less than or equal to. So I got to highlight the equal sign, alpha less than or equal to negative 0.1 x squared minus 1.4 x plus 2.1. Okay, now what? Graph it. How do I graph it? Probably Zoom 6 might be better. Zoom 6. And then most of these graphs on here you can see go from negative 10 to 10. So I have to just find the one that matches up with this. Oh, one more step though.
Oh, we got to do the shading.
Yeah, good. Alpha, shades, 1. Good. Okay, now notice in my case that, now you got to be careful about the boundary lines also, right? Not lines, the boundary parabolas. Are they dashed or solid? Well, in our case, because we're including the equal sign, we can see on here that they're solid, right? So we have to just go find the graph that matches that. So let's try to do that. Okay, none of that looks quite right, does it? No, let's try going down a little bit. Okay, we're getting there, aren't we? Is that right? What's wrong with that? There's one thing wrong with that.
It's
Got a dashed boundary, so we're getting close though, it looks like. Oop, almost. Still wrong. No. Still wrong. Uh-oh, I must have missed it somewhere. Oh, right there, isn't it?
That's the one.
That's the one. So it'd be number 12. Oops, is that 12 or is that number 6, right? 6, yeah. Okay, make sense?
Yeah.
All right. Okay, let's see what else we can see here. Whoops. Okay, next guy. Yeah, now look at this one. I'm going to go ahead and go to copied this one down. See it a little better, maybe. Okay, a projectile is launched. I put a bunch of these. They're not all going to look like this, but you're going to get at least one projectile motion problem in the text. And on the study guide, you got, I think, several, maybe. Can't remember exactly. Projectile is launched vertically from the ground. After how many seconds will the projectile be at a height of 403 on its way down? Okay, the reason this comes up is because this is a good application of a quadratic model. So here's the model we have for the height above the ground. So y is height above the ground, and then t is just the time since the projectile is launched. Okay, so we want to know then, when is it going to be at a height of 403 feet, I guess, on its way down? How am I going to figure that out? Say it again. 403 for y. Okay, good. So we're going to graph. We want to graph this model, don't we? Okay, so let's go to our calculator and go up here to y equals, and I'm going to go ahead and clear these guys out. Okay, being as I'm done with inequality, I like to not be in it if I'm not using it. It just seems like it kind of clutters things up a little bit. So I'm going to go apps, alpha, I, inequality, and then it gives me a menu, and if I hit 2, I quit. Okay. Okay, so then I'm going to go ahead and put in, now I'm going to put in x's instead of t's, obviously, right? We were using x's on the calculator. So negative 16x squared plus 599x. Whoops, there's too many 9's in there. Okay, so now if I hit zoom 6 this time, I'm not going to see a whole lot, am I? The parabola actually goes up like that, but it goes up so steeply that you can't even see it. So that's probably, zoom 6 probably isn't the best idea on this. What we might do instead, now what would be the logical starting value for t or x in our case? And when are we starting the stopwatch? 0, right? So we might as well start. Let's go to the window, and let's start at x minimum equals 0, how about? And then we're just going to make an estimate. How long is this thing in the air? Well, we don't know. We have no idea, really. Let's, how about if let's just start off by saying, I don't know, say 100 seconds maybe? And we'll just see what happens. If I put in 100 for x max, I have no idea what the y scale should be. But the calculator does a good job of figuring that out for me. If I just hit zoom 0, zoom fit, it'll think a little bit and it'll calculate the y values. Well, it looks like I went too long, didn't it? That's 0 and that's 100. And so it looks like I went way, way too long. I probably could just go like maybe, I don't know, 40 or something. You want to try that? So window, x min is 0, x max, let's make 40. And now I'll go zoom 0 again. See what happens. That's a little better. Okay. So what am I looking at there then? Y is the height above the ground. T is, or x is the time, right? So that's when it's right on the ground. I'm shooting it straight up in the air, and as time passes, it's going to get up to its highest point and then come back down to the ground. And then if it kept going, it would be burrowing into the ground after that, right? But that's really where it stops. It hits the ground. Okay. So that's projectile motion. Now, we want to know when it's at 403 feet, and Lacey had a really good idea. Why don't we just graph a line at 403 and see when they intersect, right? So we'll go up to y equals, put in y equals 403, graph, and there it is. Okay, this thing gets pretty high. That's 403 feet right there. So we want to know when it passes through that intersection on the way down. Right? This is on the way up. That's on the way down. Make sense? Okay, so how do we find out where those two curves cross? Intersect, yeah, intersect. And we did something like this. Was it? I think it was yesterday. We did one sort of like this, right? So we'll just go second, calc, 5. But we can't just hit triple enter this time. We don't just have two lines here. We've got a curve, and we have to be more specific. We got to tell it Which intersection are we looking for? So is that the first curve? Yes. Is that the second curve? Yes. But now my guess needs to be accurate. So I'm going to go over here and put the cursor close to that intersection. And it tells me that happens at x, or t for us, equals 36.752. And I think we just want to enter this to two places. So 36.75. Okay. Make sense? Okay. Now, what if they had asked instead here for, how long does it take to get to its highest point? What would we do there instead? Maximum. Sure, we'd find that. We'd go second calc maximum and find the x value of the maximum. Okay? X being t, right? And that would tell us the time it took to get up to the highest point. What if they wanted to know how high it went? That'd also be maximum, wouldn't it? But then we'd be looking for the y value. Does that make sense? So if we did second calc maximum, and I found what the vertex was of this parabola that opens down, the x value would be the time it took to get there, and the y value would be how high it got. Right? Does that make sense? Okay. All right. So be ready for a projectile motion problem or two. Okay. Moving on. Okay, what about this guy? Everybody read that? Is that too small? Make that bigger. Oops. Okay. There. How's that? So for the quadratic function in intercept form here, we want to know if it passes through these x-intercepts, negative 5, 0, and 4, 0, and the other point, negative 1, 10. We want to know what's the value of a. Okay? So how could we do that? These are problems we did in 5a, remember? How do we do these? Yeah, if we want to solve for a, in order for us to be able to solve for a, we would have to be able to plug in values for all of the other stuff, right, to know what a is. So where does the other stuff go? What are p and q in this case? Say it again. No. Negative 5 and 4. P and Q are the x-intercepts, right? So negative 5 we could put in there, and 4 we could put in there. Now what about the values of x and y?
Is that negative 1 and 10?
That would be negative 1 and 10. That's just some other point that's on the function, though. So if it's on the function, it's a solution. It's a value of x and y that would have to work, right? Because it's actually a point on the curve. So 10 would go in for y, and negative 1 would go in for x, and then the only thing remaining is a, so I can just solve for it, right? So what do I get if I do all that stuff? Let's see, I'm going to get 10 for y equals a times the quantity x is negative 1 minus negative 5 times x, which is negative 1 minus 4. Right, and I just solved for a. So what is, let's see, negative 1 plus 5 is positive 4. Negative 1 minus 4 is negative 5. So I get a times negative, positive 4 times negative 5 equals 10. And let's see, I get negative 20. So 10 equals negative 20a, so what's a? Negative 1/2. Sure, if I divide both sides by negative 20, there it is. Okay. And I think they wanted us to round our answer to 4 decimal places. Well, negative 0.5 is all we need. Terminates, right? Okay? Questions on that? Good? All right. Let's see, and then I think we're getting right down to the end here. Okay, what if the last two are almost identical? In fact, if we can do one, we can do the other. If the quadratic function whose graph passes through the points negative 6, 2, 2, negative 11, and 3, 4 is expressed in standard form, what is the quadratic coefficient A? How would we do that? It's good. Now this is going to be the stat, and then what are we going to do? Stat, calc. Oh, it's different on yours. Oh, that's right. That's right. Yeah, we're just going to put these things in, these three-ordered pairs, into the stat editor. And remember that 3 points defines a parabola. So we'll put those in L1 and L2, the x values in L1, y values in L2. And then we just go stat, calc, quadratic regression, right? It does it for us. How about that? Very nice tool in calculator. Now, notice that that question and this question then are essentially the same thing. One difference in the way the answer is going to turn out, but not the way you do the problem. If I use quadratic regressional analysis to find the best fitting parabola for these 4 points, I do it the same way, right? I'm just going to put in 4 values instead of 3. Now the difference is the parabola is not going to fit these 4 perfectly, probably. There's just going to be one that's going to pass near those 4 points. Because 4 points is 3 points defines a unique parabola. 4 points, we could have one that's off the parabola. Does that make sense? It's like if we took 2 points, there's only one line that goes through 2 points. But if I took a whole bunch of points up there and found the best fit line, well, the line might not actually pass through any of those, right? It's the same way. We do it the same way, though. Just enter all this stuff into the stat editor, quadratic, second calc, quadratic regression, hit go, and then it's going to tell you what are the coefficients A, B, and C. We want to go through one of those?
No.
Just real quick. Let's do this top one just a little quicker, and then we'll be done. I won't do the last one. Let's just quickly look at that one. Just take a second. So, stat, edit, and then let's see, we're going to go negative 6 for my first x value, 2 for my second x value, 3 for my third, and 2 for my first y value, negative 11 for my second, and 4 for my, and 4 for my third. Okay? Got all my ordered pairs in there. Then I'll just go stat, calc, 5. I'm going to go down and there it is. Okay, so we wanted, in this case, A. So A to 4 decimal places is 1.8472. Okay? Make sense? All right, very good. Okay, let's go. I can see where we have a lab.